So welcome back to our seminar, and today Roghayeh Maleki is going to tell us about distance regular graphs that support a uniform structure.
Thank you, Maria, and thank you everyone for attending my talk, and a special thanks to the organizers of this seminar that invited me to present my talk. And I would like to mention that this work is a joint work with my mentor, Shefko Miklevich, and two of my colleagues, Blas Fernandez and Juicy Monzillo. And okay, for my talk today is in fact consists of two main parts. In the first part, I will define what I mean by a graph to support a uniform structure. And in the second part, I would like to present you some of these classification results that we have obtained. So to that end, we will analyze three cases, non-bipartite distance regular graphs of negative type. By negative type, I mean the parameter q is less than or equal to -2. Also, non-bipartite distance regular graphs with classical parameters q equals 1, and the last case for q greater than or equal to 2. Let me start with some preliminaries. First of all, we assume that our graph gamma is simple, finite, and connected with vertex set x and edge set r, and partial of xy is the distance between two vertices of the graph, and eccentricity of x is the maximal distance between x and y for vertices y in graph x. And we define the diameter of the graph to be maximal eccentricity of x for any x that we take in the vertex set x. Also, gamma of I is the set of all vertices of the graph, which are distance I from vertex x. And in particular, we denote the neighbors of x with gamma of x. And for an integer k greater than or equal to 0, we say that the graph is regular with valency k whenever the cardinality of gamma of x equals k for all x in x. Here, of course, we again have the adjacency matrix of the graph. We all are familiar with that. And we put the 1 in the position xy of the matrix A if x and y are adjacent, and 0 if they are not. And V is the vector space over the complex numbers, consists of all column vectors whose coordinates are indexed by the vertices of the graph. And M sub x of C is just the matrix algebra over complex numbers, consists of all matrices whose rows and columns are indexed by vertices of the graph. And the entries are from the complex numbers, and V is our standard measure. Okay, here I would like to define my Terwilliger algebra. For that, we need to define the notion of dual idempotence. We fix a vertex of the graph with eccentricity E of x, and for I between 0 to eccentricity of x, we let EI star denote a diagonal matrix, which is defined as follows. In this diagonal matrix, in fact, if you take your adjacency matrix AI and the row corresponding to vertex x, you take that row and put it on the diagonal, and you get this matrix I star of x. So this is just a diagonal matrix, and the diagonal comes from here, in fact. And we call it the dual idempotence of gamma. Now we can define our Terwilliger algebra, denoted by T of x, with respect to a fixed vertex x, which is a sub-algebra of the matrix algebra over complex numbers. This algebra is generated by the adjacency matrix of the graph gamma, and also the dual idempotence. Now, of course, when we have this Terwilliger algebra, this algebra acts on this vector space V, and this allows us to define the notion of a module. So here we have a T module, which is a vector subspace W of V, invariant for every element of the algebra. Okay, this notion of irreducible T modules are in fact very important in our research. What I mean by irreducible, it means that it has the module has no non-trivial submodules. So we let W denote an irreducible T module. And W is in fact the orthogonal direct sum of non-vanishing subspaces EI* of W. Here we can define two important notions of this irreducible T module. Endpoint of W, which is nothing except just the smallest index I for which EI* of W is non-zero. And also we can define the diameter of this W, which is the number of i's for which EI* of W is non-zero minus 1. And the other notion that is important here is a thin irreducible T module. We say W is thin whenever the dimension of EI* of W is less than or equal to 1. Sorry. Okay, there is another notions that I need to define here: raising, flat, and lowering matrices. These are defined as follows, as you see here. The sum of some EI* AEI stars again. And these are in fact matrices in our terwilliger algebra. And the reason is that these are all generators of the algebra. So obviously these are in our algebra. And here is also a more combinatorial definition of these raising, flat, and lowering matrices. For the flat matrix, we define this entry zy to be 1 if z and y are adjacent and the distance between x and z and x and y is the same. Also, for the raising matrix, we say the entry zy is 1 if the distance between zy is 1 and the distance between xz equals xy plus 1. And I forgot to write the lowering matrix. The lowering matrix here, you just put a minus for that and you get the lowering matrix as well. So these matrices, as I mentioned, they are all in our terwilliger algebra. And the transpose of the flat matrix is itself, and the transpose of the lowering matrix is equal to the raising matrix. And it is not hard to see that they all sum to the adjacency matrix of our graph. Okay, now I would like to define the uniform structure for bipartite graphs. It all goes back to 1990 when Paul Terwilliger defined this notion of uniform posets. And later in around 2000 something, Paul Terwilliger and Štefko Miklóvič extended this definition to bipartite graphs as follows. We assume that gamma is a bipartite graph. Fix a vertex in your vertex set and define the following partial order on X. And then this allows us to directly translate the definition of uniform poset in the setting of bipartite graphs. Okay. Now, still to define a uniform structure, I need to define one more notion, which is a parameter matrix. Sorry, I have a lot of definitions here. So a parameter matrix U is in fact a tridiagonal matrix with entries on the diagonal. We have all ones. So let me just give you a picture of that. So on the diagonal, you have all the way down 1. Upper diagonal, we denote it by EI+. Lower diagonal, we denote it by EI-, and the rest are 0. So EII is 1, EII minus 1, which is EI-, is non-zero, or EI minus 1 EI, which is, if I'm not mistaken, EI+, these are non-zero. And also the principal submatrix must be non-singular. So for convenience, as I showed you here, we denote this by EI-, this one by EI+, and we have these two extra conditions. So with this in hand, we can in fact define our uniform structure. So we let gamma be a bipartite graph. A uniform structure for the graph gamma with respect to a fixed vertex X is in fact a pair UF, where F is just a vector in C to the current eccentricity of X, such that this equation is satisfied on EI* of V for I between 1 up to eccentricity of X. So now we have the definition of uniform structure for bipartite graphs. And here we have a very important result by Paul Terwilliger that says that if you have a bipartite graph gamma and fix a vertex, you define your terbilegar algebra with respect to that fixed vertex X. And if you assume that your gamma admits a uniform structure with respect to X, so this is our assumption, then the following assertions hold. First of all, every reducible T module is T. This is really important for us. Later you will see in our result that we use this fact a lot. And also the isomorphism class of any irreducible T module W is determined by its endpoint and its diameter. Okay, now I would like to extend this notion of uniform structure to non-bipartite graphs. So we consider non-bipartite graph gamma and fix a vertex, and we define Rf to be the set of all vertices of the graph in which you remove the so-called flat edges. So imagine you fix a vertex in your graph and the distance, let's say X, and then the distance between Y and X and Z and X is the same, and Y and Z are adjacent. And then you remove the edge between Y and Z. So you do for all such vertices in your graph. In fact, by doing that, you are removing all odd cycles in your graph, and you make your graph bipartite. So we define this gamma F, some people call it full bipartite graph, it depends, to be the graph with vertex set. So the vertex set stays the same because we didn't touch the vertices of the graph, we just removed those flat edges. So we have the same vertex set, and the edge set, we call it Rf here, and we observe that our gamma F now is connected and bipartite. And so we say that the graph gamma support a uniform structure with respect to X if gamma F admits a uniform structure with respect to X. So this was our definition for non-bipartite graph that support uniform structure. And now I would like to talk a little bit about the properties of this graph. So again, we assume that this is our eccentricity of X, the terbilegar algebra of the graph gamma F. Then, as I said, X stays the same for the vertices, vertexes of the graph gamma F, and this vector space V is in fact the standard module for gamma F again as well, because we didn't change any vertices of the graph. The flat matrix of the graph gamma F is 0, and so we have the adjacency matrix of gamma F to just be the sum of raising and lowering matrix. And for any I between 0 to eccentricity of X, we define the I and dual idempotent of gamma F to be again the same as before, UI star. And so now our terbilegar algebra TF is generated by the lowering flat and this dual idempotence. And here we have the connection between a T module and TF module. We let W be a T module, then W is also a TF module, and if W is thin irreducible T module, then W is again thin irreducible TF module. And here, yes. Sorry, I can't hear you.
Remind me, what is a thin module?
We say a module is thin. I think if I'm not
you defined it. I just forget.
So the dimension of EI star of W is less than or equal to 1.
Oh, okay. Okay, thank you.
Yes. And so, okay, here, as I said, this is the connection between T module and TF module, but here I should mention that we might have some cases as follows in this lemma, that W is irreducible as T module, but it won't stay irreducible as TF module. So it might be reducible as TF module. And also W and W prime are non-isomorphic as T module, but they might be isomorphic as TF module. So why I'm saying that, because these two cases, in fact, happen in the case of Duke graph. And so now I think we have everything that we need, the Terwilliger algebra of the graph gamma, its module, uniform structure for bipartite graph, non-bipartite graphs. The graphs support a uniform structure with respect to X. I mean, the non-bipartite graph in this case, if gamma F admits a uniform structure with respect to X. And so what is left here to know is what is a distance regular graph with classical parameters. So I'm sure that most of us here know what is distance regular graph, but let me just briefly go over the definition one more time. So the graph gamma is called a distance regular whenever for all integers ij, let's say h, between 0 to the diameter of the graph, and for any vertices of the graph xy that you take, which are at distance h from each other, the number pijh, which is equal to the cardinality of the vertices x at distance, vertices that are at distance I from S, intersection the distance vertices that are at distance j from y. This intersection is in fact independent of the choice of x and y, and we call it these intersection numbers of the graph gamma. And we can also denote these parameters pijh by ci, ai, bi as usual. And also we have the ki, p0, ii, and we say that our graph is bipartite if and only if ai equals 0. And here I also need to give you a definition of a near polygon. Maybe this definition for some of you is a little bit different from what I'm saying here, but this is what we needed and it was useful to us, and it was from the book of BCN. So a distance regular graph gamma is called a near polygon whenever ai equals a1 ci for I between 1 to the diameter -1, and also gamma does not contain the complete multipartite graph K1, 1, 2 as induced subgraph. So this is the definition of near polygon here. Now we can define what we mean by distance regular graphs with classical parameters. So the graph gamma is said to have classical parameters d, q, alpha, and beta. Whenever the intersection number of gamma satisfy these equalities, here you see that here you have your alpha, d, beta, and this is just binomial coefficient that we have it here. And here our q is an integer different from 0 and -1. And just to make sure that here q is really integer and it's not 0 and -1, the proof of this part is in the BCN book, Brar, Cohen, and Niemeyer. So we know that our q is not 0 and -1. And I believe that this is my last definition here. So let gamma denote the distance regular graph, non-bipartite with diameter d greater than or equal to 3, intersection numbers bi, ci, and the eigenvalues theta r. So the graph is called tight whenever we have equality in here. All right. So I think I'm done with the definition in this part, but here I just want to give you some idea that from now on, in all of our results, we have these assumptions. So we assume that our graph is distance regular non-bipartite with diameter d greater than or equal to 3, intersection bi, ci, eigenvalues theta r. We fix a vertex, we define our Terwilliger algebra, we have our dual idempotence with respect to fixed vertex x, we have our lowering, flat, and raising matrices. We can define our Terwilliger algebra for our induced for our full bipartite graph gamma f. And now we can start our first part of classification. I divided into two parts. First of all, the negative type, which means q less than or equal to -2, and then I go for the q equals 1. All right, so we have our graph, non-bipartite distance regular graph with classical parameters of negative type, and we want to know which graphs gamma in this category will support a uniform structure. So in order to that, we divided our analysis into 3 parts. So first of all, we assume that intersection numbers of gamma is non-zero and it is not a near polygon. Then we assume that gamma has intersection number A1 equals 0, and also we consider the case gamma is a near polygon separately. So I go briefly on each of these 3 cases. I didn't include all these proofs, but some of them maybe I just included to have some idea about that. So before I proceed, we have this nice proposition by Maleki in 2009 that he said, if you assume that your graph gamma is of negative type with A1 is non-zero, and it is not a near polygon, then one of the following holds. Up to isomorphism, there exists a unique irreducible module with endpoint 1, which is nothing. So we always have this one. And let W denote a non-thin reducible T module with endpoint 1, which we know it exists. Pick a non-zero vertex, non-zero vector W in E1 star of W. Then these vectors form a basis for our module W. Okay. So with this in hand, we have our first result. So assuming that gamma is of negative type, A1 is non-zero, and it's not a near polygon, we showed that the graph gamma does not support a uniform structure with respect to X. Here is the sketch of the proof, but before I start the proof, I just want to remind you of 3 important things that we already talked about. First of all, we say that gamma support a uniform structure when gamma F support the uniform structure. And then we say that every T module is also a TF module. And there was a very important result by Paul Terwilliger that says, if you assume that your graphs support a uniform structure, then every irreducible module is thin. So we have these 3 important results from before. Now here, I want to show that my graph does not support a uniform structure. If you remember, this graph is non-bipartite. And I know the result for the bipartite case. So I switch to the case of gamma F. So I take an irreducible T module in my gamma F, and I show that it won't stay thin. So that means my graph gamma F does not support uniform structure with respect to X. And using this one, the first part, I can say that the graph gamma, in fact, does not support uniform structure with respect to X. So this is the whole idea of the proof. So now let's take W to be non-thin reducible T module with endpoint 1. This type of module exists because of this result by Maleki, and it is unique. So we take such a irreducible T module, and we pick a non-zero vector in E1 star of W. Here, keep in mind that W is again a TF module because of this fact that I already mentioned before. And we let W prime be contained in W as irreducible TF module, and contains also this little W, this vector W. And we use the action of lowering and raising matrices on the basis from this previous proposition. I didn't include the actions here because they are very long and complicated. So, and then we observe that these vectors RW and L+R square W are in fact linearly independent. And here I should mention that W is in E1 star of W prime. And when you raise it, you are in the first constituent E1 star of W. When you raise it, you go to E2 star of W prime. So you are in E2 star of W prime here. And here, when you raise it twice, you go to E3 star of W prime, and you lower it once, you go back to E2 star of W prime. So they are all in E2 star of W prime, and they are linearly independent. So that means the dimension of E2 star of W is at least 2. So that means, by the definition of thin module that I already told you before, that means my W prime is non-thin. So this means that I took an irreducible T module W prime, and I showed that it is non-thin. So that means my graph gamma F does not support a uniform structure. So this means that the graph gamma also does not support the uniform structure with respect to X. So this was the whole idea of the proof. I hope it was clear. And all right, so I move to the next result here for the case when our intersection number A1 is equal to 0. Here again, we show that the graph gamma does not support a uniform structure with respect to X. The idea is very similar to the previous case. And for the last case, when gamma is a near polygon, we use this nice classification of Ching Wen Wang in 1999. And so here he assumed that if gamma has classical parameters with the diameter big enough, greater than or equal to 4, remember Q is less than or equal to -2, A1 is non-zero, and C2 is greater than 1, then one of the following cases hold. And doing some computation results, we came to this conclusion that because we computed beta, and we noticed that beta doesn't satisfy this part, and also this part doesn't hold. So we showed that in fact these two last cases do not hold in our case, and the only case that holds for us is the first case. So this gives us our first corollary here, that assume gamma has classical parameters. Suppose it is a regular near polygon with Q less than or equal to -2, then gamma is a dual polar graph, this one, or the diameter of the graph equals to 3. So for this case, that the diameter of the graph equals 3, we in fact didn't work on this part because we didn't know that the graphs that we have in this case are all graphs that we might have or no. So that's why we restrict ourselves to d greater or equal to 4. So we do not have the case d equal 3. Maybe I would say this is still open. And so for the case of dual polar graph, we have this result. So assume that the graph is a dual polar graph. Then we showed that this equation, which was given by Varabonatai in 2013, is satisfied on EI star of V. And so the graph supports a uniform structure with respect to X. Here, what we did, we used the definition of uniform structure. We computed our uniform matrix U, and also we showed that the principal submatrix P is non-singular, exactly what we had in the definition of uniform structure, and everything holds. So that means the graph gamma supports a uniform structure with respect to X. Okay, we are done with the negative case. Now we move to the case Q equals 1. For this case, we were lucky because we had this nice classification of distance regular graphs with parameter Q equals 1, which was given in Brar, Cohen, and Niemeyer's book. And so it says that if your gamma is distance regular with classical parameter Q equals 1, then it will fall in one of these 5 infinite families or graphs. And it is either a Johnson graph, Gaussian graph, Hamming graph, half cube, or Doob graph. We analyzed each of them separately, and you see that I wrote tight in front of some of them. And the reason is given in the next theorem. So we were able to show that if our graph is a tight graph with classical parameters q equals 1, then it does not support a uniform structure with respect to x. So when it is tight, it does not support a uniform structure. So we were able to eliminate a lot of cases in here that does not support a uniform structure. We are left with few cases that we check them all separately. Okay. So this is our corollary that says if gamma is one of these families or graphs, then it doesn't support a uniform structure just because it is tight, and we already proved that tight graph does not support a uniform structure. And for the Johnson graph, when n is greater than or equal to 2d, I should exclude this equality here because for n equals to d, we already know that the Johnson graph is tight and it doesn't support uniform structure. But for n strictly greater than 2d, we were able to show using some other results that the graph does not support the uniform structure. We move to Hamming graph, HDN, with n greater than or equal to 3. And we show that this uniform equation, let's say, it is satisfied on EI star of V. And so in that case, again, as previous time, we went over the definition of uniform structure, and we showed that our uniform, and we computed uniform matrix, principal submatrix, it was non-singular, everything works well. So the graph does support the uniform structure with respect to X. And for the half cube, when n is odd, because for the case even the graph is tight, we already know what is going on. We assume that n is greater than or equal to 3, and this is the diameter of the graph. And this, again, uniform equation is satisfied on EI star of W. This coefficient EI minus, EI plus, and FIs are big, so I didn't put them in the equation here. So again, it does support the uniform structure with respect to X, just using the definition as before. And I think this is the last case of Duke graph. As you know, this is just a Cartesian product of n copies of Cherkani graph and m copies of K4, where n greater or equal to 1, m greater or equal to 0, and it has a diameter 2n plus m. Again, this equation holds on EI star of W, and the graph, in fact, supports the uniform structure with respect to X. And there was another alternative proof for this Duke graph, and we showed that in this full bipartite graph is in fact isomorphic to the Hamming graph, and we already know that for the Hamming graph, the graph supported uniform structure, so it was easy to see that really the graph also supported uniform structure with respect to X. And just a page of summary of what I have covered so far. Yes, so for the negative case, only dual polar graph for d greater or equal to 4 support the uniform structure. For q equals 1, the Hamming graph, half cube, and odd, and the Duke graph all support the uniform structure with respect to X. Now, this part of the classification really wasn't that hard for us. The hardest part is the second part of the classification when we move to the case q greater than or equal to 2. Still, a little of that is open, and we are working on that. So for this part, we in fact focus on the concept of local graphs, and we had to put more assumption in the beginning to make progress. So from now on, we let the graph gamma be a distance regular graph with classical parameters d, alpha, q, and beta. D big enough, q greater or equal to 2, fix a vertex. And here we assume that the graph gamma support a uniform structure with respect to X. This is important, so we have this assumption. Moreover, we assume that every reducible T module with endpoint 1 is thin. We will see later why we have this assumption here. And this notion of local graph is nothing except just a graph that is induced on the neighbors of the vertex X. And if W is any thinly reducible T module with endpoint 1, then E1 star of W is, of course, a one-dimensional eigenspace for E1 star, A1 star, whose eigenvalues are known as the local eigenvalues of W, and in fact belongs to this set. And here, there is a known fact about the eigenvalues of this thinly reducible T module with endpoint 1, this W. And this, thanks to Terwilliger, again, we have this eigenvalue. There are 4 of them. And when we are in this case, these eigenvalues of thinly reducible T module is in fact equal to the eigenvalues of our local graph delta. And so we could show that among these 4 eigenvalues, 2 of them cannot happen, and we can have only 2 eigenvalues, and also this valency of the graph. And knowing this fact, along with some other assumption, we were able to show that delta is connected to strong irregular graph with this eigenvalues. So this is this valency of the graph. This I call it R, and this I call it S, because later you'll see why I call them R and S. So we have this connected strong irregular graph with these eigenvalues. And we could show that, assuming that, again, alpha is non-zero, we need to assume alpha is non-zero here. We computed these parameters beta, n, k, mu, and lambda for this local graph delta. And then we used this theorem by Niemeyer in 1979. He said that if G is a strong irregular graph with parameters n, k, lambda, and mu, and the eigenvalue valency, positive eigenvalue, and negative eigenvalue, assume that S is less than -1. That's why I showed you here, this is my S, because we already know that Q is positive, and so this is the negative eigenvalue here. That's why we denote it by S, because we use this theorem later. So if we have a strong irregular graph with these properties, then at least one of the following conditions must hold. Either R is less than or equal to this quantity, or mu equals squared, or mu equals S times S plus 1. And so we could show that for our local graph gamma with these eigenvalues, A1 and this eigenvalue and this negative eigenvalue, the case 1 of Niemeyer theorem, that means this case cannot happen. So we can have only these 2 cases, and these 2 cases, in fact, led us to have these 2 infinite families of distance regular graph with classical parameters, which might support uniform structure. We will see later that they in fact do not support the uniform structure. So we have these possibilities. And for the first family, this is our alpha, Q plus 1. We show that the family of distance regular graphs with classical parameters in the beginning, first slide, I assume that it supports the uniform structure. We show that they do not exist. So the reason is that, first of all, for D greater than or equal to 6, we show that the intersection number P633 is an integer only when Q equals 2 or 4. So that means in general, we cannot say it is an integer. And also the multiplicity of the second eigenvalue is not an integer. These are the requirements for our distance regular graph. We must have the multiplicities integers. So that shows that this does not hold, and so the graph does not support uniform structure with respect to X. For the next family, we observe that if we have this little condition in the beginning that D is not congruent to 0 mod 6, then the family of distance regular graphs with classical parameters where alpha equals Q, this does not exist. And the reason is that, again, we checked and we noticed the multiplicity of theta 2, which is the second eigenvalue of the graph, is integer only when D is even. So again, we have restriction. And the second thing is that multiplicity of the third eigenvalue is integer when d is congruent to 0 mod 6. So that shows that this family in general does not exist. But if we have this congruency here that d is congruent to 0 mod 6, or alpha equals 0, we could say that this can be a family of distance regular graph with classical parameters that support uniform structure. So that's why we were a bit suspicious about this. So we started to work on this and see for different diameters, let's say diameter less than or equal to 3000, we checked that, and we noticed that the valency KD and the multiplicity FD of the eigenvalue theta G, they are not integers. So that's why we came up with this following conjecture, that there does not exist any distance regular graph with classical parameters this, for Q greater than or equal to 2 and D greater than or equal to 4. And we are thinking that if our conjecture is true, then we have only distance regular graph with classical parameters that support uniform structure with respect to X only when alpha equals 0. For the case Q greater than or equal to 2. So this is our conjecture. And let me see what I wanted to mention here. I think that's everything. So I end up my talk with this conjecture that we have, and this is almost a complete classification for distance regular graphs with classical parameters that support the uniform structure. I would say we are still working on this case, but really computing this multiplicities, proving that they are not integer beside by computer, but it's hard to really prove it that they are not integers. They are long and complicated, so that's why we stop for now, but hopefully we can fix it, or if someone is interested in this talk, maybe they can also help. That's all from my side for today, and thank you very much for your attention. Thank you.
Well, people are thinking, you say they're classical parameters. Does it imply that there are other kind of non-classical parameters?
Yes. As far as I know, there is another family of distance regular graph that they are called Q-Raka type, something like that. The classical parameters and Q-Raka type families. So there, at least I know that there is another family of them. Yes.
Oh, I see. Okay. Yeah. And when you were proving all of those results, where do you get the intuition? Do you just do the calculation, then see where it brings you, or you hope that, like that? Yeah.
Which results you mean? Like,
well, the results in the middle of the slide somewhere.
You mean?
Yeah.
If I'm not mistaken correctly. You mean for the second case that Q greater or equal to 2?
No, for all of the Qs, you were considering different things, right?
It's just an interesting question that my mentor also worked on this area, and he suggested to work on this topic, so we all worked on that.
Okay.